please join me in welcoming to the Distinctive Voices podium, along with his RapidTech team, Dr. Marc Madou.
Thank you for the introduction, and good evening. As you can see, this is not going to be your usual talk. It's a bit more complicated, so you will have to do some multitasking here. So over there on the table, what you're actually looking at is, on this side here, is a 3D printer where we can print these 3D objects. And as we speak, Ben Dolan from RapidTech, one of the directors there, is now printing out a design for the National Academy of Science seal here, this one. So by the time he's up explaining what he has been doing, he will have produced that part. You also see on the right here, that machine, what that does is it laser scans an object. In that case, you see this handle here. This handle will be laser scanned. The information, the image will go into a computer and then sent to this machine to make another one of those, right? Anyways, that's explaining the setting, okay? So now my talk is about a scenario, very importantly. I'm not that arrogant to claim that I know the solution for a very big problem that this nation is facing, the loss of manufacturing. And so I urge you all to kind of just think about what does it mean if the United States would not make things anymore that are advanced in nature, that people from other countries come to the United States for because they were looking up. Their father or grandfather said, everything is made in America. But it's not true anymore. So, and then, of course, my colleagues from RapidTech, there's 3 directors here, actually, Ken Patton, Ed Tackett, and Ben Dolan. And so it's an NSF center that's tasked by the National Science Foundation to do teaching and outreach to the local industry to teach them all about this 3D printing. That is their mission. And so they are now on our campus, and we are integrating our research with that institute. Okay? So that's the background. What I will cover is, first of all, my own motivation. We all kind of stumble into something. In my case, I'm a nanotechnologist, a micromachining guy. So what motivated me to get so intrigued with the future of manufacturing? I will tell you a little bit about that. Then I will tell you what I think we need to do in terms of education. I think we need to re-engineer engineering. You see, making physical parts, manufacturing, has become a little bit like a dirty word. Everything was virtual, it's all software, and no one really has a good feel anymore for making product, for making devices. And I think it's a philosophy. It's kind of a disdain for anything that's real. And I think we have become a society that become so virtual that we have virtually nothing. And that's kind of... My third bullet point, I forgot the bullet points, but it's the third line. One thing that you hear a lot about, it's all over. You see it on television, you see it here on stage, is this 3D printing, rapid prototyping, additive manufacturing. It's all the same name for what we're going to tell you. What is all this hype about? Because indeed, it's a little bit, it's fantastic, it will do a lot of things, but it's overhyped. And so, after you see what we can currently do, then I will tell you it's not good enough. We need to go beyond what we can do with these machines today. And you can see the machine is working here already. You see it's printing a new one of those, right? But you know, we cannot make small or big things in the same object. So it's not multi-length scale, not multi-materials, multi-physics. I will explain more what I mean with that. So, but it's short right now. It's not good enough. And then I come to my conclusions. I'm not too certain that I should start with this rather depressing image here. But read with me what people are predicting about the United States and manufacturing in our country. In 10 years, the only manufacturing left in the United States will be defense industry, industry that are very high tech, those that cannot afford long distance freight charges, and 4, those industries that service on the spot instantaneous demand. Although maybe even that is questionable. Think about that. Right? So, my motivation. How did I start getting into this? Well, in 2004, 2005, I was asked by this organization here, WTEC, which stands for World Technology Evaluation, to go throughout the world. We were with 10 scientists from the US, go to Japan, Korea, Taiwan, and try to figure out in manufacturing, micromanufacturing, is the US still leading? Or are we running behind? The purpose of that is that then the agencies, the funding agencies, know if they should fund more in that area if we are running behind. Right? And so here we wrote a book about our findings. You can find it on the web. And we also testified in 2005 on Capitol Hill. And so basically here is our conclusion. And you can debate that, but that's what we found. And I think it's pretty urgent. We need action. So countries that are not manufacturing high technology goods anymore are increasingly at a disadvantage. See, they do not gain anymore from the next product implementation. You see what we saw over and over. You would go to Samsung, for example, and you would be brought in a room. None of these products are made in the United States anymore. Sometimes it's already a second or third generation. And in the US, people would still say, oh, don't worry. We will still design it. We'll still market it. And that's what we say is not true. Because you don't lose linearly, you lose exponentially. And so it's very hard to pull that back once it has left your shores, the manufacturing. Because the new materials you gain insight in the new products, that information doesn't feed back to you. Also, intellectual property is much stronger close to the product than in the inception stage. You know, at universities, we invent something, but it could be 10, 15 years before actually someone physically implements it. And so for all of these reasons, I do believe that manufacturing ought to be brought back on shore. There's more motivations that have arisen more recently. We all know that Obama's Advanced Manufacturing Partnership, has been announced. A first pilot institute was awarded in Youngstown, Ohio. And in the State of the Union address, three new institutes were announced. And so one of the motivations of myself, together with, can you believe it, for the first time perhaps, we have created a coalition that pretty much has all of the universities, all of the national labs unified. So can you imagine a California response with Stanford, Berkeley, UC Irvine, Lawrence Berkeley, Lawrence Livermore? We are going to talk about that tomorrow in the president's office in UC in Oakland to consolidate this further. But this probably would be, you can see how important people start thinking that this whole thing is, right? That such a group of people can come together. Then maybe a final point I want to make as a scientist about my motivation. Look at this curve you're seeing here. This is the loss in manufacturing jobs between 2001 and 2009. 1/3 of jobs in manufacturing were lost over an 8-year period. And you know what is so strange for us from the science point of view? You cannot believe how exciting it is right now, actually, to be a scientist. There's nanotechnology, there's carbon nanotubes. We can write letters atom by atom with an atomic force microscope. We make MOSFETs that have critical dimensions below 22 nanometer. And this somehow, our research findings is mostly not resulting in more workforce. And you know it's worse. The government investment in R&D is leading to profits elsewhere because we cannot even implement anymore our own inventions. Why? We are missing that step between research and actually product development. Right, so I hope I have given you some idea of what motivates a lot of people currently about manufacturing and how to bring it back. I told you that I think a key here is to re-engineer education. If you look about the state of education, and I'm now kind of focusing a bit on California, we have higher and higher tuition for what is perceived by many, actually perhaps less value. That's a problem. We have more and more unequal access to education. Third point, a very important one. Lack of skilled US technicians. There's some foreign companies here that can actually not staff it. They don't have the skilled technician. And that has a lot to do with the fact that we kind of have the 4-year colleges and 2-year colleges so separate. There's no continuity. There's no talking. In a way, the society has become so separated. And I think our education needs to heal that. We need to have continuity of students going from 2-year colleges to 4-year colleges and talk to scientists so they can help and be the technicians of the next generation equipment invented, perhaps, in the 4-year colleges. And also then, in a way, the science of making things got lost in many areas. People don't know what's in their cell phone, and most of them don't care, right? But if you don't care, you will also not be involved probably in the next generation iPhone. And unfortunately, Samsung starts really coming after us on the iPhone, isn't it? There's a sign there. There's also then systemic, outside university and education in general, there's some indifference to employees, outsourcing, little interest in making real things, same point coming back. Loss of manufacturing base is loss of innovation. I tried to make that link that IP is stronger, closer to the product. And the middle class is disappearing in lockstep with the loss of manufacturing. This actually will lead to future threats. For example, if the US doesn't make the next best thing anymore, do you think that the best students will continue to come to the US? They will not. If they see that most of these products now are generated somewhere else, and you're a good, ambitious engineer, you're going to say, I'm going to go there, because they make the latest product. So even our education could be in danger if we don't do something. The gap between fewer rich and many more poor will continue to increase, and then security concern, right? If we don't make the next best chip, we might have to outsource or buy the chips from our enemy to fly our aircraft. Enough about that. We are doing something, okay? So I'm sorry if this sounded a little bit like a downer so far. We are energetic and we are positive, and this is the US. We will implement something that I think needs to still fit what we have as a major advantage in the US. So I'll come to that. If you're getting depressed, wait, hold on a little bit, okay? So concrete, at UC Irvine, for example, these are some of the efforts that we are doing in terms of educating people and getting back into manufacturing. Actually, bringing a RapidTech onto the campus was part of that, to have our engineers being closer to manufacturing. Because think about it, what are we doing here? We have the design and we manufacture it. If the loop between design and manufacturing is closer, there's no reason to ship it out, right? You can do it all here. So other points. We are connecting back 4-year colleges with community colleges. And those community colleges are in turn better integrated with K-12, K-12 grades. We are trying to give as broad a group of people as possible access to rapid prototyping, this kind of machinery. I invite you after this lecture to go see what's actually going on and make an appointment at RapidTech to get a feel of what this technology can do. When we do that, we believe we will unleash creativity, because the IP in manufacturing is much more potent. We are shortening the design to prototyping, from prototyping to product, and we are thinking more and more, and now this is the concept that starts kind of, in terms of technology, we think starts making sense. We believe that if manufacturing would be much more distributed, so that not every house, but maybe every Kinko's on the corner of the street can print you goods, can print you products, right? That means distributed manufacturing. Instead of having big companies with equipment that's way too expensive to afford for a small company or a mid-sized company, we are having many, many cheaper workstations to build things, right? That is kind of one avenue we see as an opportunity, distributed manufacturing. We also are working with our students on project engineering competitions. There will be a little video on that, and let me tell you a little bit about what that video is. We want to make our students enthusiastic about making things again. So one of the classes I'm teaching is this: make your professor drunk. What I mean with that? They see the machinery like this, and they know the plastics that we can use, the materials, and I ask them to design a bottle opener. And every time they succeed to open the bottle without breaking the bottle opener, I drink the bottle, right? And so you'll see in the video towards the end, okay? Because students are getting good. They're starting to figure out, oh, I should not make the bottle opener like this. If it's weak plastic, I should do it like that. Huh? Little things like that. Design and material, it all is hooked together. We also now are changing the materials and manufacturing technology concentration on our campus into a department so that we actually start getting back in producing engineers in manufacturing. And then, as I told you, we have RapidTech on campus. So, we want to build on US strengths to do that re-engineering. We're going to work on the flexibility, the risk-taking, diversity, imagination, space, and resources. Coming from Europe, that is still aspects that are very hard to find, but in California and in the US. So I believe that this kind of thing fits perfectly because it's based on ingenuity, individualism. You don't need a big group to do it together. You don't need huge investments, so distributed manufacturing. We have to invest in education, new manufacturing materials, and build the next generation of manufacturing tools and methods. That is what I will give you towards the end of this presentation. Now, this is, I think, what we need to invest in. Now, to give you a little bit more of a concept and an analogy of what we think we want to do in advanced manufacturing in this country. Think about a computer. A friend of mine here from the University of Urbana-Champaign, Placid Ferreira, has sketched on the right-hand side a manufacturing system, a manufacturing operation, and on the left, a computing system. And he points out that actually each element in a manufacturing process finds it equivalent in a computer. And so he feels that it ought to be possible to take the same principle where people used to work on mainframe computers, and there were very few, to a desktop computer. We will do the same in going from huge factories to small desktop factories. That is kind of the concept here. But it will not only be these kind of machines, additive manufacturing, we need more for that. And that comes in my talk a bit later. So now, I gave you a bit of the motivation. I told you a little bit about how we need to change engineering education. Now we're coming a little bit to the hardware. And here, I will try to simplify a little bit. You don't need to read everything on the board there, because there's a little bit too much information. I want to explain about how this rapid prototyping works before we actually then explain what's going on right here. And it turns out that there's a lot of jargon out there and all means the same. Rapid prototyping, computer-controlled moldless additive manufacturing, 3D printing, layered manufacturing, digital manufacturing, all of that is kind of based on the following principle. You have an XY stage. You see that stage right here that's moving. Can move in an XY direction. It also can move in a Z direction. And in the Z direction, there's a platform that can move up and down. All of this equipment has the same simple concept. Before you walk out, go past this little machine there, and you'll see all that there is to it is this platform that can move up and down, and then an XY controller. That's all it is. And that allows you, maybe some of you people remember that, this was a cover of the economics. This thing was printed. This is a violin, a Stradivarius, and it plays. The part that was not 3D printed, strings, thank you. You got it. From all of the techniques out there to do that, I cannot explain all of them. I'm going to explain how fused deposition modeling works, 3D printing, and stereolithography. So are you with me? We're going to do a little bit of physics, not much. I'm going to try to make it as simple as possible. for the moment, ignore this graph. If you're interested, what it basically says is how much it costs, how big a thing I can make, and how fast it is, depending on these technologies. But don't worry about that. We will start with the very simplest method for us to make one of these 3D shapes you're seeing. And by the way, this is all indeed about 3D printing, right? So instead of printing your business card, look what I have here. This shape that it's like a puzzle, can do all of these 3D movements. This is printed in one go. So this did not need to be assembled afterwards. So this additive manufacturing does things that there's no way you can do with other manufacturing. So I'll give this around. Ed, can you catch this? There we go. So this thing was printed with this machine. And how does it work? Well, I'm kind of really lucky. I have this machine here, and here, and here, right? And so, for one, you see this platform here. That is the platform that can move up and down. And then do you see these plastic wires here? You have two in this case. In this machine, I only have one. And this plastic wire goes through this heater here. It melts, and it's deposited on the platform. So let's say I have one level, and I make one layer. I make the design. What I do next is I lower that platform, and again, a new layer. Lower it, a new layer. And so I have my 3D object. In this case, you can see it only has a white plastic. In this case, a bit more sophisticated. I have a blue one and a white one. One of the two can be dissolved out. So it's sacrificial, so it kind of is a support material. And so that allows you to make these most intricate things, things that are hollow, things that you really can't figure out how you otherwise would make it. If you use your imagination, you can make things that are impossible to make with any other techniques today. It sounds good right now, right? But you'll hear a little bit later, but, right? If it sounds too good, it's usually not true, right? So here are some of the objects made. Can you imagine making this in metal? Or this? Wouldn't work, right? And this thing, we are printing structures out in 20 minutes, an hour. Not bad, right? So fused deposition modeling. Think about it a little bit like toothpaste that you're squeezing out, except in our case, it's these wires that we heat and put on a substrate in layers per layer per layer, right? You got that one? Good. Next one. Oh, but by the way, before I go there, is there machinery out? Yeah, expensive machinery and cheap machinery. Like this one is an expensive one. Could cost about 120,000, 140,000. But then we have machinery that does the same, that costs about 5K or less. So I don't know, Ben, how much does this one cost? 1,500, right? So still an expensive printer, but not that expensive anymore, right? By the way, one of these printers replicated itself recently. Well, not that recently, so May 2008. That's true, you're laughing. That's the parent and that's the child right there. Okay, now we go to the next one, right? 3D printing, 3DP. How does this one work? Okay, Z-Core, good, but it's been bought up. Because things are going fast in this field. How do we do this? So before we had this plastic wire. In this case, we have a powder. And the powder is in this reservoir right here. I bring this piston up, and then some powder that spills over is brought with this roller onto this movable platform. Same platform again like there. But now, what I do, I come in with an inkjet printer with a little bit of glue. And the inkjet printer will only glue the powder together where it needs to make a solid shape. And so again, it does it layer by layer. The inkjet printer goes over the shape you're drawing this layer. I load the platform, more powder, do the next one, and I draw anything I want. Look, you see here how the shape comes out of the powder, out of the machine, right? And many of these shapes are shown right there. This is good for colored kind of shapes, like this guitar, these molecules, this feet. This is all made with this 3D powder printing, so to speak. So wires, powder. Oh, and by the way, the last kind of slide on this, this is all made in one go. Can you imagine that? and you push one wheel, all of these wheels start moving. Imagine making this with any other technique. Unimaginable, right? You couldn't do it, right? So now, third one. So you remember first one, squeezing out the toothpaste. Second one, the powders that we gel together with this glue. The third one is perhaps the most sophisticated one and has the most future to be extended in big shapes and very small shapes. It's called stereolithography. How does this one work? So instead of a powder or these wires, I now have a clear, transparent liquid, but that liquid can be solidified by a laser. So if a laser hits that liquid, and again, always the same thing, you have a platform, now the laser beam hits, let's say, this point, it solidifies the liquid, it becomes solid. That is, right? You can see on the date, actually, mid-1980s. Huh? Exactly, yeah. And so this technique allows you to write in 3D in this polymer liquid. You will see that there's a tremendous amount of new development on this technique, making it possible to go to the nanoscale. We will actually show that with this kind of equipment, the latest format of it, you can put little statues on a human hair with all of the resolution you can imagine. And that's not old. No, absolutely not. But so you see the principle here, right? So we have this vessel full of liquid, and again the platform, always the same, right? A platform, and then an XY stage that solidifies or melts, and then you move the platform up, a new layer comes in, you draw on that layer, and there you go. So now you kind of saw the typical thing that happens in the chemistry class, right? The chemistry professor has one test, and it always works when he does it by himself, right? But you must say we had like an 80% working here. Huh? So you saw a demonstration, and it's still ongoing, of an actual 3D printing with one of the three techniques of printing I told you about. Do you remember them? So one, FDM, right? Fusion deposition modeling, which is with these wires. The second one was powders, and the third one is in that vessel, right? It's a liquid that you solidify with a laser. Now, remember what I'm going to say you, it's not good enough. This will not bring manufacturing back to the US. Oh, yes, but you remember, I cannot cover all of these. There is, look at this. All of them are on there. E-beam, laser sintering, right? So on purpose, because we don't have much time, I selected those three examples, okay? Good. So now, look at this curve. This is a hype curve. And many people say now that 3D printing is right here on the top of the curve. And they might be partially right. We have to be very, very realistic. Because, you know, today, we don't have many materials that we can feed these machines. So we need to develop more materials so that instead of prototypes, these are functional. You remember my bottle opener? If it breaks when you work with it, it's not functional, is it? So we need to develop new materials. That's one thing. We also need to make it multi-length scale. What that means is I need to be able to do very small features, let's say nanometers, and go all the way to decimeters, right? That's multi-length scale. Third, maybe the most important one, I need to do multi-physics. This is all additive manufacturing, meaning I add material. Huh? But we think we also need subtractive. We need to perhaps polish it afterwards. So we need to bring different physics together in one manufacturing machine. Our vision is that for the United States to get back in manufacturing, we need to get back into the hardware. It's to developing these new manufacturing tools that can do these things that we're talking about here. Multi-length scale, multi-materials, and multi-physics. So why is it not good enough? This kind of proves one of the points in terms of who is currently, in terms of industry, using this technology. You can see this on this pie chart here, who's actually using it. But then it shows, look, only 10%, maybe it's a bit more now, maybe more like 12%, I would say, Ed, right, that actually, when you print these things out, they work, they are functional. All the rest is still, you know, Yoda, right? I don't think Yoda is functional. Well, if you make a movie, as Ben is saying, maybe that is functional, right? You have to think about your definition of functional. Also not good enough for another reason. This is not the first time people have been thinking about desktop manufacturing. It turns out there's actually 3 different communities out there in the world that have separately developed such concept. There is something on the right here called Desktop Factory. Desktop Factory was developed mostly in Korea, in Japan, some activity in Germany. There was only one built in the United States. What's the concept there? You all know your computer numerical controlled machinery to machine metals, lathes. Often you use these huge 1-ton machines to make a part that's that small. The concept is there, don't do that. Make it into a desktop factory. That was one community, mostly mechanical engineers doing that. Then what you heard about today is this additive manufacturing, 3D printing, like we are doing here in front of you. That's another community. A lot of people there are more maybe material scientists. They don't talk to each other. These are different communities. And then in the middle, interestingly enough, is yet another community. Electrical engineers are making mini clean rooms. So instead of having to go into a clean room, the clean room is this size. People stay on the outside. And instead of using masks, they have digital light projected chips that do the exposure of the photoresist. So over vision, the physics and the operation of these 3 things need to come together. That's when I talk about multi-physics. We call that hybrid manufacturing platforms, where you combine some of the features of these different platforms in new machinery. And so today, these stations execute a limited set of processes in a narrow application domain, and they lack shared standards. You know, there's no software across these platforms. A little bit in more detail now. What did I mean with this multi-length scale? And then to prove to the gentleman that there has been a lot of development since the early 1980s in stereolithography. What we do now is trying to expand the range of operation. You know, if you see a tree outside, a tree has manufacturing length scales over 10 to the 21 orders of magnitude, from basically molecules to the stem of the tree, which is meters. In human manufacturing, we are so poor, if we can do 3 or 4 orders of magnitude, let's say, you know, from millimeters to perhaps a centimeter, we are very, very happy. What we want to do is make it much more dynamic in length scale, multi-length scale. So we want to be able to make a structure like that artificially. We are getting there. How do we get there? Well, originally, in the early 80s, when that laser beam was hitting that polymer, the solidification unit was rather large, it was crude. We couldn't focus that laser enough. We couldn't make fine enough features. But you'll see, we are getting there. Look at this. This portion here, this is 100 microns. So we have a portion here of about 200 microns, 0.2 millimeters. This is a stent. This is actually a functional product. This is not very functional. So what we've done is gone from the 80s, millimeters, we have gone to hundreds of microns. It hasn't stopped there. We are now doing this. See that? This is a human hair. This is a Venus de Milo statue. There's 3 of them. This is done with a process called 2-photon lithography. By the way, this is a process that was projected to be possible by Einstein. The idea is if 2 photons, let's say 2 photons of 800 nanometer in wavelength, hit a dye molecule in your photoresist or in your vessel with your polymer at the same time, they act as a photon of 400 nanometer, double the resolution. And so we can write directly in that 3D bath and write anything, these spiders, these kind of things. So we have gone from nanometers to microns to millimeters to centimeters. Multi-length scale. Huh? We need to be able to do that before we will have real manufacturing stations that serve a broader purpose, than the current additive manufacturing allows us to do. This is a machine, I'm not going to go into detail, we call it DIMS, it means Desktop Integrated Manufacturing Platform. It's where we combine the stereolithography from the 80s with the two-photon lithography from today, and then that way achieve multi-length scale. Materials. You already noticed that we can print some of these plastics out. We have certain powders that work. We have that polymer bed that you can solidify. But you know, most of these materials are not strong enough. Like, you know, my bottle opener, most of the time it will crack, it will break. So there's a tremendous need for material studies, way beyond the ones that are currently used, to allow this number of real products. You remember I told you there's perhaps 3%. If I go back to this number, I think my battery is off. It says 10%, right? If we can develop new, better materials, we perhaps can bring this to 30 or 40% of functional goods. So that would help in real manufacturing products. Turns out that's actually something magically about this 3D printing and an additive approach that allows us to make new materials. So not only do we need to provide new materials for the current equipment, this kind of equipment allows us to make architectured material. Some of you might have seen this metal here. This metal lattice is the lightest metal lattice ever made. Thank you, Ed. I said, how does that work? I got some help from the audience here. Now, how do you make that material? Well, you actually make it with additive manufacturing. So now imagine that you have a metal, instead of one density, I can have it give it a gradient. I can make it more dense at the outside and lighter in the middle. So I can make architectured or structural materials. So it kind of goes both ways. We need to make more materials to feed into these machines. Then these machines can make us other new materials, structured, architectured materials. We also need to develop things like composites to widen broadly the application range of this 3D printing. And finally, this multi-physics. And this is a lot of jargon there. Just look at me, this is Muzak again. What is the multi-physics? I already told you, right? You're going to use not only additive manufacturing, where let's say you put this powder down and melt it together or glue it together. You will also cut it, polish it. So that's a subtractive force. So you let on that piece that you're making, your work piece, you act with different physics on it to make your final product. We also need to develop the software that can drive equipment like this. That also doesn't exist yet. Thank you. This will help for my conclusions. So I hope you've learned some new stuff tonight, right? At first, I told you this kind of dire picture of the US needs to get back into manufacturing. Then I told you we need to work on education. We need to change the mood of the country in terms of making physical things is a good job. Manufacturing is not a bad thing. And actually, manufacturing will require a higher level of education than it used to, because it's much more integrated with design. Then I told you, well, there's this 3D printing that's today on the top of the hype curve, right? And maybe it will do a lot of good things, but be careful, right? For three things. So you remember them? Three things we are falling short on. Not enough materials to make functional goods. The next one, multi-physics, right? And the third one, so multi-materials, multi-physics, multi-length scale. So if we can do these three things, I don't know if it was you or you who answered, but you're right, multi-length scales. If we do that, then imagine the following world. Advanced manufacturing at the point of need. In the hospital, you need a knee implant. And you're on the bed. You don't want to wait for a week on the bed, right? It doesn't fit. So we need to retry it. That's a good example, right, of point of need. Military, a ship that breaks down, like recently that disaster. Military in general. Point of need is a good first initial place to try these things out. So having an on-site HiMap, so that's that hybrid manufacturing platform, that's my name for it. It would allow to benefit organizations that require small numbers. Say you have that vintage car, and there's that one part that's not made anymore. Yes, your solution is easy, right? You only need one or two, you can have it printed. These are good solutions, a good application. Let's say a small number of custom or specialized parts, such as hospitals, aerospace firms. I know we can come up with a lot more situations where this is of use. Another scenario, manufacturing as a service at the mall. This is, in a way, starting to happen a little bit. Young entrepreneurial people are setting up kind of like 3D Kinkos, right? You lost your key, or you want to have a key with your name on it, or spoons for a party with a family name on it. That kind of thing can absolutely happen already, right? So manufacturing as a service at the mall. HiMaps, these hybrid manufacturing platforms, might be implemented by entrepreneurs who install manufacturing facilities for consumer orders. That's comparable to today's print shop, and able to produce prototype models, short runs of 3D objects, and single replacements of parts on site, like the lost key we were talking about. This third bullet point is kind of thinking about the internet. You can well imagine that within California, we have this 3D printing station that does, let's say, you were talking about laser sintering. You need a metal part. And then that part has a certain specification that you can do. Over the internet, you send that specification to the other facility that can do that kind of manufacturing step. The part is shipped there and finished in that place. So that's like a collaborative effort that could go very fast because we all work from the same specifications, same software, etc. And then the last bullet point, personal manufacturing. You know, these very inexpensive ones, we can now buy some of those, I believe, for $300, $500, right? So that could provide, you know, at home, you could print your next Christmas decorations, artists, etc. Don't laugh at it, because that's where often inspiration comes from for the next generation products. So just like the computer, the microcomputer, didn't reduce the number of jobs, it gave this tremendous boost to the economy, because suddenly everyone could edit, do his own thing on his small computer. The same thing we envision could happen with this new HiMap. Not this yet, it's not far enough, but the next generation. So I hope you will all encourage people you know around yourself, family, children, to get into this area, to not be totally enamored with everything virtual, just programming. Tell them there's something good to be said about making things, and find fun in making things. And with that, I'd like to thank you, and you can ask questions.